All right. So in the last class, we were talking about different data types, primitive data types. Let's continue our discussion on this primitive data types. So in primitive data types, so we talked about integers. So we have int, signed and unsigned integers. And then we can have, like short or default size, long size integers. So, and then we have float, double, and long double. And then we have char, and then underscore underscore. So if a variable is of type integer, or if an object, if you take an object, if it is of type integer, um, and so depending upon if it's a signed integer or an unsigned integer, there will be a suitable encoding for it in bits. Because no matter what we are talking about, finally, these are all encoded in the form of bits. These are all encoded in the form of bits. And there is a specific, for each of the data types, there is a specific mapping function. There is a specific mapping function. Like, for example, if you take a floating point value, something like pi or something like that, any floating point value 3.14, it needs to be encoded as a sequence of bits. It needs to be encoded as a sequence of bits. And so what happens is in the program, when we use these decimal numbers, no, they will be mapped to equivalent floating point numbers, into equivalent floating point number representation underneath, and vice versa. So we have mapping functions from which take us from here, from decimal to binary, and binary uh, to decimal. And so this is what is called as a representation of a floating point number in the computer. And there are different standards for it, IEEE floating point representation standards for it. And similarly for long, double, for double and long double, etc. So in this class, we will not we will not try to make an effort to understand how these numbers, these floating point numbers or double or long double numbers, are stored in a bit format representation or stored in a binary format. All right. And on the similarly, uh, for integers, we will take a brief look on how integers are represented, and what's the mapping function that is used to represent integers. But again, we will not delve into the details, but I will give you a high-level view of representation of integers underneath. So if you take just int, let's start with unsigned int. So unsigned int, uh, so it is represented using 4 bytes or 32 bits in the computer. 4 bytes or 32 bits. And the value of so what is the mapping function? So let me use a mapping function. This let me use the name as binary to decimal, which takes this bit vector B0 B31 to B0 to B31, and the value associated with it is this. Okay, so that means this bit has value 2 power 0, and the next bit has value 2 power 1, and the next bit has value 2 power 2, so on and so forth. Let's say, for example, if we are working with 4-bit numbers, the value of this is 2 power 0, the value of this is 2 power 1, and the value of this is 2 square, and the value of this is 2 cube. And so you multiply this bit with this one, and then you finally add it. So the total value of this will be 2 cube plus 0 plus 0 plus 1, which is equal to 9. So this is translation from decimal to binary to decimal. But how do you translate something from decimal to binary? That is also something we will see in today's lecture. Are you with me so far? Yes or no? Doing good?
Yes, sir.
So now let's look at signed representation. Signed. So let me use the subscript binary to decimal u, indicating this is unsigned, and we will have another function binary to decimal subscript I will use yes to indicate it is a signed. In fact, there are many ways of mapping, but the mapping that is used in practice is what is called as a 2's complement representation of numbers. So in the 2's complement representation of numbers, the most significant bit B31 is called as a sign bit, and its value is equal to the weight associated with it is minus 2 power 13. So if the sign bit is equal to 1, so if you are representing, remember, if it's an integer, if it's a simple integer, you can represent positive numbers and negative numbers. And whenever you are representing positive numbers, B31 bit will be equal to 0. So B31 bit is equal to 0. So is equal to 0. So let me not use this mix up things. We are using math. So this is equal to 0 implies the number is positive number. Whereas B31 bit, if it is equal to 1, then it implies the number is negative number. So for example, one way of checking whether a number is positive or negative is by looking at the most significant bit, and if it is equal to 0, then it is positive number. If it is equal to 1, then it's a negative number. This is what is called as a 2's complement representation. You will study about this in a different class again. So I'm just giving you some kind of intro to this. In the digital systems and microcontrollers course, I guess you will study this. And later on in CSO course also, you will study this more. But so if it is, if you are working on 4-bit signed numbers, then the value of this becomes, minus 2 cube. This is 2 square, 2 power 1, 2 power 0. So this number becomes minus 8 plus 0 plus 0 plus 1. This is equal to minus. So the same 1001, so the same 1001 If you interpret it as an unsigned number, then what happens is it becomes, its value will be equal to 9. And if you interpret it as a signed number, its value becomes uh, -7. Are you with me here so far? Good. So now let's try to see how this kind of works by writing a small program. So I stop the screen share and I am seeing Siddiq's Mission Impossible picture. Good, good one. Okay. Yeah. So let's hash include okay. Let's see. Parshva has this question: what if the number is positive but big, so that most significant bit is equal to 1? So Parshva, in that case, you get into what is called as a overflow situation. It's a very good question. When you add 2, so see, given that we are using uh, 32 bits, there is a range of numbers you will be able to represent. So if I am right, so let's say, let me look at this. So where is that? Are you able to see my Visual Studio Code? Sorry. Share screen. Okay. So Parshva has this very nice question. I use this opportunity to explain a bit more. Uh, so if you are working with, this is important uh, when you are writing programs, because this is where some very serious bugs can happen. So if you are working with unsigned numbers, so what is the, and if so you use 31 bits, what is the maximum value you can store? What is the minimum value you can store for unsigned integers? It is 0. What is the maximum value? When all the bits are equal to 1, right? Sigma I is equal to 0 to 31 2 power I times 1, when all the bits are equal to 1. This is 2 power 32 minus 1, na? Or 2 power 31 minus 1? This is 2 power 32 minus 1. Okay, great. So this is the maximum value you can store. This is the maximum value you can store. So what happens is, like when you add, let's say, when you try to add two numbers, let's say you are adding 2 power 32 minus 1 and uh, with 2 power 32 minus 1. So when you add 2 power 32 minus 1 and 2 power 32 minus 1, what do you get? You get a value 2 power 33 minus 2, right? Yes or no? When you add them together? Yeah, I guess so. So, yeah, then, yeah, so it cannot fit in. So what happens is we get into what is called as a overflow situation. This is very, very dangerous. Overflows are dangerous. Imagine, so you, in your bank account, so you have, you deposited some, you already have some $1 million and you deposited a couple of more $1 million, and, and the variable is not able to hold your richness, and overflow happens, and weird things can happen for you. So Yeah, so let's see. Yeah, let's see. There are a couple of things I want you to understand from this program. So number one, so let's say you have, let's declare an unsigned integer. Unsigned integer. And specifically, I am using, I can directly assign a a binary value to a by saying like 111, 111, 1. These are 8 ones are here. I guess so. Okay. Thank you. Thank you, Mukund. So I'm assigning 32 bits. And all the bits are 1. And let's say I print this unsigned I is equal to %u and signed I is equal to %d / n I. So that is when you say 0b, that means whatever that is coming out, we are directly assigning a binary thing. Okay, that all whatever the bit pattern that is there after that, it will be directly assigned to I. That is a binary notation. Does it make sense, Vaibhav? So now let's compile this program, GCC overflow. Yeah, it will be from right to left. Did you see the value of I? Did you see the value of I? When it is interpreted as a unsigned number and when it is interpreted as a signed number? So the point here is, the first point here is when there is a bit pattern, so that bit pattern by itself doesn't mean anything. How we interpret it is what matters. When we interpret it as an unsigned number, then the function that is applied is this. The function that is applied is this. But when you interpret it as a signed number, the function that will be applied is minus 2 power 31 plus sigma I is equal to 0 to 30, 2 power I into 1. What is its value? So this is equal to, this is minus 2 power 31. This will come as it is, plus this is equal to 2 power 30 minus 2 power 30, or yeah, 2 power 31 minus 1. When you this summation value, so this and this gets cancelled, so you get minus 1. Are you all with me here? Yes, no? So now I have one interesting, yeah, and then, so yeah, who asked for this question? So when we add two really large numbers, positive numbers, and if the resulting positive number doesn't fit into that range, then bad things can happen. No, so the way, what is the 2's complement function? If you interpret this as a 2's complement number, then what happens is the most significant bit value is minus 2 power 31, and the rest of the bits, their value is is obtained by summing them up. Sigma I is equal to 0 to 30, 2 power I into 1. This summation is 2 power 31 minus 1, and this is minus 2 power 31. When you add them together, finally we get minus 1. So when you treat the same bit pattern using the 2's complement function definition that we have seen before, and we get the value minus 1. Are you with me here? Yes, do you understand this? Your system doesn't crash, Siddiq, nothing like that. Okay, you end up getting bad answers, incorrect answers, and that can lead to serious problems, bugs in your program. No, you could be a semantic error, or no, something happens, and finally, depending upon what you are trying to do, like for example, in the earlier case, so you added $2 million to your account, but instead of having $3 million, you have some other value. In fact, no, what can happen? In fact, what can happen is, I will give you an interesting example. So let's say you have in your account this much amount of money. Are you with me? Are you all with me here? Can you? This is the amount that you have in your bank account. Okay, so this is yeah. Let's say for some reason, so there is a bad programmer who used. Or let's say, what's the big deal? So he's not a bad programmer. So this is the amount you have. Okay, this is this much amount you have in your bank account, and then so let's see. You say, hey, I am rich. So this guy is fantastically rich. He has a lot of money, and then along you came, and you said, so take my $1, and or maybe he gets greedy on the way to the bank. He sees a $1 note on the road, and he gets greedy, and he goes to the bank and deposits that $1. Okay, so now, so he deposited $1. And then he says, sorry if I'm just having some and then, so now he prints his uh, so how much money he has after depositing one more dollar? How much richer he is? Sukhjinder, he is richer by $1. Let's see if he got richer by $1 or not. What should I use? Okay. I am not sure how to split this string into two lines. And so anyway, so let's compile this code. Yeah, he is on the road now. So you see the problem. So this overflow can do disastrous things. Overflow can do disastrous things. Uh, when you are writing programs, if you don't understand how these things work internally, then you could get into serious trouble. Worse, the worst thing is this. Okay, so the programmer is actually, uh, didn't use unsigned integers. He wants to use, he thought, yeah, what's the big deal? No, he got used to writing programs. Uh, so he got used to writing, no, just using int everywhere. So he just did this one, and let's see what happens. Okay. So now can you tell me what happens when I run this program? Yeah, so from being a millionaire, he becomes, not only bankrupt, he has to pay a huge amount of money back to the bank. Are you with me here? so you, so from a millionaire, he turned into person with massive amount of loan to pay back. In order to, Sukhjinder has this question, how this is happening. Yeah, so in order to understand what is happening, uh, yeah, so you need to know a little bit about binary arithmetic, but broadly what happens is you enter into what is called as a overflow condition. All right. Yeah, the mechanism of overflow I will explain. So let's go back to our whiteboard and see what happens. So let's say, in how do you know how binary decimal arithmetic happens, right? So uh, in decimal arithmetic, let's say if you are adding 123 uh, to 247. So what is 123? 123 is equal to no 100 plus 2 tenths plus 3 ones. Yes or no? 100 plus 2 tenths plus 3 ones. And 247 is 200s. I'm sorry if you feel bad that I'm teaching you this, but that you are learning this from your, gray UKG, LKG, or I don't know, whatever. So how do we add these two? So you add these two. So 3 ones and 7 uh, so 3 ones and 7 ones, it is 110, right? So what do you do? So you write this 110 here. Okay, you put this 110 here. And and then there are no zeros here, and there is only zero zeros. Okay, sorry. So this zero ones. Okay. And 6 tens, 4 tens, 6, 2 tens and 1 10, it is 7 tens. And 200 plus 100 is 300. So the result is 370. Are you all with me here? Doing good now? So it's very simple. But let's say if you are using, this is 947, then what we have here is 9. So if you do the same arithmetic, what happens is 900 and 100. So 900 plus 100 is 10 hundreds. Okay, what is 10 hundreds? It's 1000, right? So it is you will have to put one t. So this is 0,000s. This is 0,000. So you put this 1000 here, and you have 0,100. But unfortunately, in the place, you don't have a place to write this 1000, so it gets lost. So now instead of getting 1070 rupees, you have only 70 rupees in your pocket. Does this make sense? How overflow happens? At least for unsigned numbers. You don't have place to put that 1000, so it's gone. So, and so now when we try to do the same stuff in binary, so what is in binary? Let's say 1010 0010. So you know the place values, right? So this is 2 square. This is 2 power 1. This is 2 cube, 2 square, 2 power 1, and 2 power 0. So you have, so the way it works is you have 1 2 cube is there. Exactly. So yeah. So and then if you see one, I'm just explaining in the last class, you told you don't know how to do binary arithmetic, but I'm explaining you how to do binary arithmetic now. So here, this number 1010 is nothing but 1 2 power cube, okay, and 0 2 squares, and 1 2 power 1 and 0 2 power 0. Imagine there is a different world in which currencies are not in terms of ones, tens and hundreds. It's in terms of ones, twos, fours and eights. This is the currency that someone use in some particular world. So now, so what do you do? So you have, if you take this one, you have 0 2 cube and 0 2 square and 1 2 power 1, sorry, and 0 2 power 0. Okay, so there is a world in which the currency is in the form of 2 cube dollars. Okay, so whatever, 2 square, I don't want to give the names, but anyway, you understood the point. Okay, so now what do? You want to add these two numbers. So when you take 0 2 power zeros and 0 2 power zeros, you get 0 2 power zeros. But when you add 1 2 power 1 and 2 2 power 1s, you get 2 2 power 1s. But 2 2 power 1s is nothing but 2 square. So that gives us 1 2 square here and 0 2 power 1s. So here you write, and 1 2 square and 0 2 square plus 0 2 square is 1 2 square. And you have, and 1 2 cube and 0 2 cube is 1 2 cube. And this is nothing but 1 1 0 0. Does this make sense, guys? Are you all with me here? So this one is coming here. Are you all with me? Yes, no, maybe? You all understood how binary arithmetic happens, na? So now, how does overflow happen? So now, let's say you have 1 here. So if you have 1 here, then similarly, the way it happens before, uh, so here everything else remains the same. No, and when we come to 1 2 cube plus 2 2 cube, you get 2 2 cube, but 2 2 cube is nothing but 2 power 4. So you have something like here 0 2 power 4 plus 0 2 power 4 and 2 power. So this will leave us with 0 2 cube and 1 2 power 4. But the problem is we don't have space to store the last 1 bit associated with 2 power 4. So your 2 power 4 is gone. It gets sunk. That's it. And that's what exactly happened when we initially, that fellow has lots of money. Okay. In fact, he has the lot of money and that's the max the bank can hold. And then no, he got greedy on the way and added $1. So now what happens is, it just keeps going, and the final value he get is 1 followed by all zeros. Okay. And this is gone. This got sunk and he became a pauper. Okay. Are you all happy so far with the discussion? Okay, good. So now what I will do is for the rest of the 10 minutes, I will take 10-15 minutes. I will review this idea of base conversion. Okay. Negative overflow, Vaibhav, it requires a bit more effort, but I'll still give a quick explanation. So let's say you are working with 4-bit 2's complement representation of numbers. So in 4-bit 2's complement representation of numbers, so what happens is this is how you compute the decimal value. Yeah, that's true, Vaibhav. That's what I'm trying to tell you. So, 2 times B1 plus B0. Okay, this is 2 power 0 times, this is 2 power 1, this is 2 power 0 times B0. So what happens is, let's say when we add 2 numbers, okay, when you take 0, 1, 1, 1, its value is 2 power minus 2 cube plus 0, 2 square into 1, 2 power 1 into 1 plus 2 power 0 into 1. So now to this, he added 1. So when he adds 1, so minus 2 cube 0, just added $1. So what happens is when you add 1 2 power 0 with 2 2 power zeros, you get 2 power 1. Okay, that is 2, right? So 2 is nothing but 2 power 1. So you put 2 power 1 into 1. So you are adding a extra 2 power 1 here, and you have a 2 power 0 into 0. Yeah, same. So and now 2 power 1 plus 2 power 1, it is 2 power 2. So you have something like 2 power 1 into 0, and you have 2 square into 1, and 2 square 1 into 2 square 1 is 2 power 2 cube. So what happens is you will have a 2 cube uh, one here, and here you will have 2 square into 0, and then you have 2 cube. So now this is when we add these two, we get 1001, all one followed by all zeros. But unfortunately, what happens is, no, in the 2's complement representation, this value is equal to minus 2 cube, so you got into a negative. Okay, this side. Great. All right. So now I will give a general discussion on bases and also on hexadecimal representation. So there is one question. See, I want to ask this question to you. Let's say we are working on unsigned numbers. We are working on unsigned numbers. B31 to B0. So this can, using these bits, you can store values from 0 to 2 power 32 minus 1. This is a range of values that we can. So if you take an arbitrary number I in this range, let's say if you pick an I in this range, this I, you can represent it in binary form, or you can represent it in decimal form, or you can represent it in hexadecimal form. So they are all equivalent to each other, but the representation or encoding of I is different. Because there is a question whether the range sometime at the beginning of the class, whether overflow depends upon the representation of numbers. No, not at all. The range is fixed. 0 to 2 power 32 minus 1. We are representing that, we are putting that range in a decimal form because that's what we are comfortable with. But the representation could change, but the value of I is not going to change. So this is the world in which all human beings, no, we are all happy because we are taught arithmetic here. So human beings, all human beings, okay, all human beings, we are all happy working with decimal numbers because that's what we are taught. But computers, where everything is, where we realize things using transistors and switching circuits, they are happy in the binary form. Okay, but there could be some other world, some other planet in which they are very happy. People are happy working with hexadecimal numbers, and so they may be looking like this. Okay, so they are happy with hexadecimal numbers. So depending upon, so like for example, maybe if you give a problem to someone who came from this alien planet, so as soon as you give the problem in this form, but he will immediately convert it into his form and solve the problem, and then communicate it back to you in the language which you are comfortable. Does this make sense? Like for example, down the lane, you may design computers using devices which can encode just not 2 states, but maybe 16 states easily. Then maybe you are better off working in the hexadecimal space rather than working in the binary space. All right. I hope you are able to appreciate the discussion in today's class and in the last classes, because these are foundations. I just want to focus on foundations in the rest of the lectures in this course. Foundations, foundations, foundations. That's what I want. I want these things right. So now let's take I will conclude this lecture with a discussion on base conversion. So let's say you have a number 843 in base 10 representation. So its value is 8 into 10 square plus 4 into 10 power 1 plus 3 into 10 power 0. Post this class, I will give you one more video of mine in which I kind of, it's a long video, but you just have to watch for 15-20 minutes. Uh, uh, so that video is in one of the doubts clarification sections for section A. So there is lots of stuff, but only 15 minutes you have to focus. So I found my own discussion appealing to me. So I reviewed it and repeating the same. So it's but it came out very well. So you may want to review it there also in case if it's not clear here. But let's say if you have this is base 10. And so, but on the contrary, if you are working with, so generally speaking, if you are working with a set of, if you have digits dk to d naught, and if it's in base B representation, its value is the value associated with it is sigma I is equal to k di into not 2, sorry, into b power n. Right? And these digits, no, d naught to dk, so they belong to d naught to dk. They belong to the range 0 to b minus 1. Like for example, if base b is equal to 2, then the digits can be, so if base b is in binary form, the digits can be only in the range only 0 and 1. Right? Like for example, if you take 711, or maybe I will use a smaller number. Yes, 511 in octal representation. So the check is 5118. It's a valid thing because these three digits, they belong to the range 0 to 7. But if I have something like 911 in octal representation, this is wrong because 9 does not belong to the range 0 to 7. Are you with me so far here on this particular idea? Okay. And what is the value of 511? So 511 is sigma I is equal to 0 to, let me use a simpler thing. I don't want to use sigma. So it is 5 times 8 square plus 1 times 8 power 1 plus 1 times 8 power 0. So this is 8 square. 8 square is 64. 64 times, how much is this guy? 329. Huh? Thank you, Pratyush. I'm about to ask, but the answer came before. Great. And this is 329 in base 10. In 329 in base 10. And a popular representation is hexadecimal representation. In hexadecimal representation, the base is 16. Okay. So in hexadecimal representation, so let's go to this hexadecimal representation. The base is the base is 16. Base 16. So the digits they should go from 0 to 15. So if you want to write a digit such as one so if you want to write something like 1, 13, 0. So writing this is kind of awkward. So what do we do? So we do 0 to 9, and 10 is represented as A, and 11 is represented as B, 12 C, 13 D, 14 E, and 15 is F. So if we have a number, for example, if we have a number 1A0 in base 16, its value is 1 times 16 square plus A times 16 power 1 plus 0 times 16 power 0. How much is this? 16 square is 256, right? Yes or no? So this one, but A, yeah, you can figure that out. But A is nothing but 10. So this is 10 times 16. 10 times 16 power 1 plus 0 times 16 power 0. This is equal to 460. This is hexadecimal representation. So, Mukund has a very good question. So, using binary is understandable, but why is hexadecimal used when there is decimal? So, the way I feel is, so you have the decimal world here, and you have binary here. Sometimes hexadecimal acts as a very good intermediary between decimal to hexadecimal to binary. Working is easy. The reason is this. So let's take a number. So let's look at this. So um let's look at 32-bit numbers. So B31 to B0. So what is its value? Its value is sigma I is equal to 0 to 31 2 power I into Bi. We can do one interesting thing here. One interesting thing here is I will try to rewrite it, this summation in this particular way. That is B cube into 2 cube plus B2 into 2 square plus B1 into 2 power 1 plus B0 uh, into 2 power 0. So, and then, so this is, in this summation, these are the first 4 terms. The next 4 terms are this. B7 into, the next 4 terms also I will write like this. B7, B6 2 square, B5 2 power 1 plus B4 2 power 0 into 2 power 4. Is this all right? The next term in the summation, this whole thing, does it make sense? Because when you take 2 power 4 inside, you get B7 into 2 power 7, B6 into 2 power 6, so on and so forth. Yes or no? So similarly, you can write the same. So B7, B11 into 2 cube plus B10 into 2 square plus B9 into 2 power 1 plus B8 into 2 power 0 into 2 power 4. Are you all with me on this summation here, guys? How we are rewriting this summation? This is 2 power 8. Okay. This is 2 power 8. So if you look at the summations within this range, if you look at the summations within this range, what is the range? What is the range in which these values can come? Whatever that is there in the parenthesis, if you just focus on what is there in the parenthesis, what is the maximum value they can assume and what is the minimum value they can assume. They can take values from each of these things, they go from 0 to 15. And if you see this one, you can think of this as 16 power 0, and you can think of this as 16 power 1, and you can rewrite it as 16 square, so on and so forth. So the idea here is, if you have a binary number, like for example 1000001, if you want to convert it into hexadecimal, you just divide the first 4 bits and you take the value of it. Here it turns out to be 1, and you take the value of this 100, which is here 1, 2, 4, 8. Yeah, let me use a different thing. 1, 2, 4, 8, 10, 11. 11 is B. So B1, if you want to translate a binary number into hexadecimal number, you can quickly write it like this, that B1, you just take each of these nibbles and map it into a value from 0 to 15. And so the binary representation of this is equivalent to the hexadecimal representation of this. Similarly, if someone gives you a hexadecimal representation, you just take this one and expand it into 4 bits. You just take this B and expand it into 4 bits and put it together. So you will have the binary representation. So like for example, let's say there is a variable I, you want to initialize it to, like for example, if I initialize it to -1, then if I write like this, it becomes very easy, because this each expands to 1, 1, 1, 1. So this whole thing, variable I is set to all ones. But if you have to use binary, so the way that I have used earlier, 0B, 1, 1, 1, 1, 1, 1, 1, 32 ones, that's a pain. When we put 0x means it's a hexadecimal number. There are multiple conventions. You can use a 0h also, I guess, or 0 capital H or small h, or you can use a h after that. But if you put 0x before, then that means what follows is a hexadecimal number. Are you all with me here? I would like to conclude this this lecture, if you're all with me so far. Not necessarily. This is like a programming. So the question, so let me. So here, so now we can write something like this. Int I is equal to 0x 1, 2, 4, 7 ff. So this 7 corresponds to this. This 7 corresponds to 0, 1, 1, 1. And then we have all the f's. So how many f's we should have? How many f's I should have here, so that this is equivalent to this? So there are 8 f's, so I need to have 7 f's. 4 f's. Okay. Yeah. So now you can clearly see it's very, very easy to encode the particular bit pattern that we want on line number 6 using hexadecimal format. So many times when we are working with addresses what do we do? Many times we can see I write no like the address of this location is something like 0xf00. This is the address of this location. And then after that it is 0xf001, 0xf002, so on and so forth. So there are many kind of simple advantages. It's not like it is a necessary thing, but it makes our life quite easy. Are you all with me here? Yes, no? If you use base 64, then you have to use, no? What will happen, Sanyam? Tell me. The range is 0 to 63. Then you don't have even enough alphabets to represent the values. Not six. How do you represent 62? Then you should start using alpha, beta, gamma, whatever. So your life becomes much more messier. Right now in hexadecimal, you just have to remember A, B, C, D, E, F, and but later on you have to, it becomes a pain if you use base 64. All right. So I will stop my lecture today here. We will pick up the thread, but I want you to watch the video which explains base conversion. I will post that video. You just have to watch for 15-20 minutes. That's all, not more than that. So that way the whole story is complete. All right. Siddiq has a question. Siddiq, I will possibly take that question on a different day. Um